This was the riddle in the last video, and I forgot to give you guys the answer. Since she has collected 49 ends, how many cigarettes can she make from these? It would be 8. She makes 7 cigarettes from the 49 ends, and then she's able to make 1 more from the 7 she has just smoked. Isn't that pleasant? So she can make 8. Only the clever would have gotten that one. Well, here's another one. If 7 people meet each other and each shakes hands only once with each of the others, how many handshakes will there have been? Pause the video if you don't want to see it, because I'm going to give you the answer right now. It would be 21. Most people think 42. A shakes hands with B. B has already shaken hands with A and need not do it again. So there you go. Okay, let's move on. Test number 4, the P-series test. What you should remember before we do this is back in chapter 8 when you learned the improper integrals, that 1 over x to the p dx, this particular integral converges when p is greater than 1. All p has to do is be a little bit greater than 1. The infinite series, or sorry, the improper integral converges, and so that's really the basis behind the P-series test. Same thing, where if p is greater than 1, then the infinite series converges, and it diverges when p is less than or equal to 1. Remember that series that I told you about? 1 plus 1/2 plus 1/3 plus dot dot dot. That's plus 1 over n plus dot dot dot. Well, that n is to the first power, and see that p is less than or equal to 1. This series diverges. Okay, it's the last one that diverges because all p has to do is be a little bit greater than 1, and this is the series we just talked about. This one right over here, same one. And if by chance you were to get a, I'm just going to do another example here. We just did that. If you were to get a series, let's say n equals 1 to infinity of 1 over n cubed, and you were asked, does the series converge? You would say, by the P-series test. Okay, by the P-series test, you would say the series, 1 over n to the 3, converges, and you would say p equals 3, and 3 is greater than 1. If you want to be really technical, by the P-series test, this converges, p equals 3, which is greater than 1, check. Boom, you're done. Okay? So that's all you have to say. If you're lucky enough to get one of those series, if you just remember the P-series, all that has to be is greater than 1. Okay. And yeah, I guess that has to be, those terms have to be positive as well. So let's put a plus sign there. Let's put a plus sign here as well for the direct comparison test. And let me just check something really quickly in my notes. I just want to make sure I'm not forgetting anything. Ratio. Let's see how far we want to get. Just sing a song to yourself for the time being. And okay, we're good. Alright, the direct comparison test. You should have studied the direct comparison test in Chapter 8. Again, that was the section that I wasn't there for, so hopefully that's fresh in your mind. But yeah, all the terms have to be positive there. It says a sub n, here you go, no negative terms, and a ceiling function. So this is the thing. You've got this series, and then you've got this other series that has terms that are always greater than the one that you're looking at. So you're trying to figure out if a sub n converges. If you can find a series that converges that's always greater than this one, then this one, then the a sub n would also converge. Okay. Now, so that's a ceiling function. So that's a good way to help you guys see that. So you've got this. Let's go right over here. So we have this series that has a bunch of terms like this. All the terms are getting smaller, 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 and we're trying to figure out if this series converges. Well, if we find a series that's greater than that for every single value of n, greater than, and this particular one up here converges, then the one underneath it, everything below it has to converge. Okay? And then same thing with if, let's say, this is the one, this purple one here, you can't really probably see the color, but let's say this one up here is the one you're trying to figure out if it converges. And then you found this other series, a well-known series. It's always going to be a well-known series, one that's easy to prove that it either converges or diverges. If the one below it diverges, it sends all the other series above it diverging as well. Okay, so in other words, the one above it, if the one above it converges, then everything below it converges. If the one on the bottom diverges, then everything above it diverges. Students run into trouble when they say, look, this one up here diverges. Oh, so therefore this one down here must diverge. Well, that's not true. 1 over n diverges, and that would be up here. And this one down here, it's going to be 1 over n squared. P series, 2 greater than 1. This series converges. Okay, so you can't compare a convergent series to a divergent series. Here, if the divergent series is up there, you can't conclude anything about the one down here. Okay? So let's take a look. This particular example right here, example 5, let's look at this here. We've got 1 over 3dn plus 1. So let's say if n equals 0, then we have 1/2. If n equals 1, then we have 1/4. Then we have 1/10 plus ... Okay. Well, here's an nth term. A sub n would be 1 over 3 to the n plus 1. Now, you got to remember something here. If the denominator of a fraction gets smaller, then what do we say about the fraction itself? What happens to the fraction? So, if the denominator of a fraction gets smaller, so in other words, if we didn't have this plus 1 right here, then it'd be a really easy series to determine. What happens here? Is b sub n greater than a sub n? Is the nth term greater here or smaller? When we make the denominator smaller, it makes the fraction bigger. Okay? So we say 1 over 3 to the n is greater than or equal to 1 over 3 to the n plus 1 for all n. Okay? And so since that's the case, well, what do we know about 1 over 3 to the n? Well, 1 over 3 to the n, so we take this function here, or sorry, this series here, 1 over 3 to the n, and we can rewrite it like that, 1/3 of the n, from n equals 0 to infinity. What do we know about 1/3 of the n? Well, we know that this is a geometric series, right? That's a geometric series. So this converges, and you would say geometric series, common ratio equals 1/3. We could say absolute value, less than 1. Okay, so that's enough. That's enough to say that this series converges. So this series converges. Well, if this nth term is greater than the other nth term for all n, then therefore we would say, since b sub n is greater than or equal to a sub n, then this series from n equals, what is it, 0? N equals 0 to infinity of 1 over 3 to the n plus 1 also must converge. Also converges. Okay? That's it. That's all you have to do. That's a lot, but the concept being, we've found a series that's greater that converges. If you have a series of terms that are greater than the one that you're looking at, then, and it converges, then the other ones must also converge. Okay? So I'm going to leave example 6 for you guys to do, and then we're not going to do this one down here. We're just going to leave that one blank. Okay? And we're going to go right into the limit comparison test. I want you to do example 6, and I want you to come back in and bring that with you into class. Okay? You know, I'm already at 9.5 minutes, so let me do a new video.